Okay. Okay. We wait another minute, we are 23, then we start, okay? Another couple of minutes, the last couple of minutes, and then we start. I am already sharing my desktop, so I hope you are able to see page 10 of the file differentiation, which is general differentiation rules. If you don't see, if you do not see my desktop, please let me know. Thanks. We wait. Okay, another minute. We are 24. $25. Okay, guys. Now we start with the lecture. Okay, so we continue with differentiation. In particular, now we are going to start to review together the differentiation rules you need. Okay, so let me start. So now we do computation and differentiation rules, then exercises on differentiation rules and on other concepts related to derivatives, etc., etc. So here, guys, if you are not able to do derivative, you can use this page 10 at the beginning at least, as a table to perform the exercise. And every time you do an exercise, look at this table here. I mean at the beginning, because you must know this rule automatically. But if someone did not study mathematics by several years, or never study derivative, at the beginning you need to use this table. Okay, but then you have to be, but after having done exercises, you have no longer to use the table. You are not allowed to use the table during, for example, the exam of mathematical method and tools. So we start. General differentiation rules. So the general differentiation rules are the following. If you have D means derivative, square bracket, inside the square bracket, I wrote f of x plus minus g of x. This means the derivative of the function inside square bracket, which is the derivative of a sum, is equal to the derivative of x plus or minus, depending on the fact that here you have a plus and here a minus, what? The derivative of g of x. So the derivative of a sum in general, if you have the sum of three functions, the derivative of the sum is the sum of the derivatives of each of the functions involved. And this means derivative of f of x. The sign of derivative of f of x, the notation for derivative is also the following, f prime of x. So f prime of x is the derivative of f of x. Remember that before the break, we saw that f prime of x0 was the derivative evaluated at a specific point x0. So f of x is a function and its derivative, in general, it's a function itself. Okay, so it's a function. Then the derivative evaluated at a specific point, as we saw previously, is the instantaneous growth rate at that point, or the slope of the tangent line to the graph of the function at that point. But in general, the derivative of f of x is a function. We can denote it as f prime of x. So typically this is notation used, either derivative of f of x with the d or f prime of x, plus minus the derivative of g of x, and I denoted it as g prime of x. As always, guys, if you have troubles, let me know. So another general rule of differentiation, yes? The rule of differentiation is the following. The derivative of a product of two functions, f of x and g of x. The rule of the product tells you that you have first to derive f, so f prime of x, times the second function as it is, times g of x, plus the first function as it is, times the derivative of the second function, g prime of x. So this is the general differentiation rule of the product. So this is the formula to compute the derivative of a product. Then you have the derivative of a ratio. The derivative of the ratio between f of x and g of x. Well, first of all, there is, you have to, the derivative is a ratio. You have to take, in the denominator, you have to write g of x, that is this function, and you have to raise it to the power 2. So it's g raised to the power 2, of g of x raised to the power 2. Then you have the in the numerator, the derivative of the numerator, so f prime of x, times the denominator as it is, g of x, minus the numerator as it is, times g prime of x. Please do not make confusion between the product and the ratio, because you see that the numerator here, in the numerator here, is very similar to the derivative of the product, but you have a difference. You have minus the numerator times the derivative of the denominator. Instead, in the product rule, you have the plus. Okay, now composite function rule, or function of a function. Suppose that you have a function g, okay, which is a function of f of x. G assigns a value, assumes a different value assigns a different value to, according to a given function g, to each possible value of f of x. So if you have the derivative of g of f of x, well, the derivative is g prime. So the derivative of the function g evaluated at f of x times the derivative of the inner function f prime of x. So you have the derivative of the outer function evaluated at f of x times the derivative of the inner function. So this is the composite function rule of differentiation. Another elementary rule is the following. If you have the derivative of a constant that multiplies a function, a more general function, you can take, yes, you can say that the derivative is the multiplicative constant, so copy it, times the derivative of f of x, times, so f prime of x. So this, you see, I wrote where k is a constant. So these are the general differentiation rules. Why I called them general differentiation rules? Because in this case, you are still not able, in principle, obviously, okay, because maybe probably you know you are already able to do it, but in principle, you are not able. I still have to explain how to compute the derivative of a given function f. Well, the derivative of f depends on the kind of function you have. These are only general differentiation rules, that works for all the function f of x, g of x. But now I need to give you specific differentiation rule for the different kind of function that we studied together, we reviewed together. In particular, guys, in particular, I start from the simplest function, which is the derivative of a constant. The derivative of a constant alone, guys, not a multiplicative constant. If you have derivative of 3, which is the derivative of 3? The derivative of 3 is 0. Why, guys? What does mean 3? 3 means, for example, y equal to 3. Graphically, what is it, y equal to 3, guys? Is an horizontal straight line. Horizontal straight line. Which is the slope of this straight line? Is 0, is an horizontal straight line. In fact, the derivative is the slope of the tangent line to this function. Which is the tangent to this straight line? Is the straight line itself, and its slope is 0 everywhere. So the derivative of a constant is 0. Okay, derivative of a constant. Don't confuse the derivative of a constant that multiplies a function. Okay, so derivative of an additive constant. Now, here I built this table in this way. I reported the general rules, which are related to composite functions, and here the special cases. And very often in book, especially in high school, superiori, they start from the simplest one, but here I started already from the general and then the specific. So I called composite function and their special cases. I provided here only the rules you need with mathematical method and tools for people knowing. So I avoided composite function and simple function involving trigonometric function, goniometric function like the sinus, cosinus, tangent, cotangent. Okay, I avoided this because you will not use this function with mathematical method and tools, and because for the majority of the students these are a huge trouble because they knew nothing about sinus, cosinus, etc., etc. So to provide this rule now would create only additional confusion because they would have had to spend a lot of time to explain trigonometric functions. And I told you don't need them, so okay. But so for this reason, I report only the rules that for sure you need and you must know very well. So look at the first derivative. I called it case capital A. So derivative, this means of f of x, a function f of x raised to the power alpha. Why is this a composite function? This is a function of the type, guys, of the type g of f of x. Which is the function g? G is the raising to the power alpha. The inner function is f of x. So this is a composite function. So the general rule tells you, I read with my, I invented obviously memory, you have g prime. So the derivative of the outer function evaluated at f of x. So look, g prime of f of x times f prime, so of x. So the derivative, now I give you the rule, is alpha, copy alpha, he has a multiplicative constant of f of x raised to the power alpha minus 1. This is the derivative g prime. This is what we called g prime of f of x. But the rule of composite function then told you that you have to multiply by the derivative of the inner function, so times f prime. Okay. Okay, guys. Okay, so we go on. Oh, here something sorry. Okay. Now, which is a specific rule, guys? Specific rule. Consider the case in which specific rule is special. A special case is the case in which f of x is equal to x. Very special. Y equal to x. So this if substitute here x, and you have the derivative of x to the power alpha. Which is the derivative of x to the power alpha? Well, you can get this rule simply starting from this one, because you have alpha, copy it, then the rule tells you f of x, but in this case f of x is x. To the power, the rule tells you alpha minus 1, so to the alpha minus 1. Times what, guys? Times f prime of x. F prime of x is the derivative of x, but guys, the derivative of x is always equal to 1, is equal to 1, and I can provide a graphical intuition of the reason. Let me cancel here. Why the derivative of x is equal to 1? If you use this rule, the general rule to get the special one. Which is the meaning of derivative? The derivative in general represent the derivative function represents the slope of the tangent line to the graph of your function as a function of x itself. But y equal to x, what kind of function is? We saw it in the first lecture. This is a straight line passing through the origin. In particular is, okay, I did it poorly again, suppose this is the origin, is the bisetrix of the first and the second, sorry, the first and the third quadrant. Which is the slope, guys? Which is the slope? Y equal to mx plus q, so m is 1. So the slope is 1. Which is the tangent to the graph of this function? Is the function itself. So which is the slope of the tangent? Is the slope of the of this function itself. So the slope is m is 1, so the derivative of x is 1. So for this reason here, I did not report times 1. I mean, if you want, you can report it, but it's useless, okay? So you see that this is the general rule. This is instead a very special case, the case in which f of x is equal to x. And I told you that in books very often they report first this one, and then they generalize to this one by using the composite rule function. Now, case B, rule B, derivative of a, where a is greater than 0 and different from 1, you remember, a raised to the power f of x. So this is a general exponential function, but it's a composite function because you have the exponential function and you have that this exponential function, you have the exponential function, but here you don't have simply x, but you have a function of x. So this is a composite function. First, do the outer derivative. The outer derivative is the following. The derivative of a f of x is a f of x times what? Ln of the basis. Ln means logarithm with basis e of a. Ln of a. So this term times this one represents what we called g prime of f of x. So is g prime of f of x in this case is e to the power f of x times ln of a. Guys, in this you have nothing to understand because I'm providing you the rule, okay? Then you have to understand that by following this rule, we need to multiply by the inner derivative. That is the derivative of the exponent. The exponent is f of x, its derivative is f prime of x. Well, here, guys, since it is more spread and is almost special, I report it as this is already a special case, but it's still a composite function. Well, a case which is most often spread in mathematics, in economics, and in almost all science is the exponential function when the basis is e. And this is a little bit special for a reason, and we are going to see it. Apply the rule. Well, this is again a derivative like the previous one. If you want, you can put the parentheses, but here it was useful. Also here was useless. Okay, but since I reported above, if you want to report it, but it's useless, this parenthesis, because you don't have a sum. Okay, so it's useless here, it's useless here. And here, well, maybe it's easier to understand with the parentheses. So follow the rule above because I already provided the rule. So derive this rule by using the rule above. The rule above tells you a to the power f of x. a to the power f of x, e to the power f of x, sorry. Then you have to multiply. I wrote it here because I forgot the first time to write, times f prime of x. You see here, guys, I wrote here in green, f prime of x. Times what? ln of who? ln of e. But ln of e is logarithm with basis e of e, which is 1. So for this reason, in the special case in which a is equal to e, the formula is a little bit simplified. Why? Because you see, you still have this term, which is e to the power f of x. You still have, obviously, f prime. But since ln of e is 1, you don't see here the term ln of a. But this was still a composite function. I told you it's a special case in the sense that here, instead of having as a as a general basis, you have a specific basis e. Now, look instead at the very special case, which are no longer composite function, which should be a to the power x, e to the power x. That is, special cases are obtained by setting f of x equal to x. So, derivative of a to the power x. You can derive, it's not a new rule. You can get this rule as a special case of this one. Look at the rule. The rule tells you e to the power f of x. So, in our case, f of x is x. So, e to the power x times ln of a, which is f prime of x. F prime of x is the derivative of f of x. Okay, but in this case, we are in special cases, f of x is equal to x, which is the derivative of x. It's 1, so times 1, so you do not need to report it. Now look at the special case of this one. Derivative of e to the power, again, of x, e to the power x. Look at the rule. The rule tells you e to the power f of x. So in this case, e to the power x times what? F prime of x, which is f prime of x, is the derivative of f of x, but f of x is x. So times 1. And okay, here reported also ln of e, but okay, ln of e is 1. So you have this beautiful rule. The derivative of e to the power x is simply exponential of x. So you can derive the exponential function and you still get the exponential function. Okay. Now go on. Logarithm with basis a of f of x. Well, the rule is the following. Guys, I tell you directly the rule because it is, guys, 1, because you have, again, this is a function of a function because you have the logarithmic function and the argument of the logarithm is a function itself. So it's a composite function. The function g is the logarithm with basis e, and the derivative of the logarithm with basis e is 1 over f of x times logarithm with basis e a of e, and then you have to multiply by following the rule g f prime, the derivative of the argument. So you can write it directly as f prime of x over f of x times logarithm with basis a of e, with basis a of e. So here is ln of the basis, here is logarithm with basis a of e, so pay attention. Now, special case, well, it's very special case as the one above is the case in which a is equal to e, the Euler number. So we have in this case derivative of logarithm of f of x. You can get it immediately. I mean, this has in principle nothing special, so you can apply the rule of above. We have this rule, so f prime over f of x. Then you have logarithm with basis a of e, which is the basis here, e. So you should have log with basis e, but log with basis e can be written as ln of e, ln of e. But ln of e is equal to 1. So you see, this rule follows immediately from this one. So it's not really, these rule are not new rules. They follow immediately from this one. We applied, to get this one, we applied the one above. To get this one, we just applied this one. And all the columns here or rules are not special rule because they all come from this one and this one, if you want. In particular, special case associated to this one. The case in which f of x is equal to x. So we have to compute the derivative of the logarithm with basis a of x. You have f prime of x. Which is f prime of x, guys? In this case, is the derivative of x, which is 1 over f of x. F of x in this case is x. So x times logarithm with basis a of e, copy it. What about this one? Derivative of ln of x. Look directly to the final result, to this one. F prime of x is the derivative of x, which is 1. F of x is the argument x, so 1 over x. Okay, with the theory, I hope and I think that for today we finished. Now you should now we're going to do practice with this rule to review how to use this rule, because I repeat, these rules are fundamental. You must know them quickly. You must be able to do derivative immediately. You cannot be not able to do derivative in the course of mathematical method and tools. But here you have a lot of practice. So we start easily. We start by looking first one rule at time, so we can make practice. Then we will see function in a mixed order, so you need to be able to recognize the rule you need to apply. So now exercise, use the elementary rules. Derivative of f of x to the power alpha, which is equal to alpha to f of x times f of x to the power alpha minus 1 times f prime of x, or directly the really special formula, which is the derivative of x to the power alpha, which is alpha times x to the power alpha minus 1. That is, we are going exercises that requires application of these rules, of the one in the first row. Okay, either this one, I mean this one can be always applied, but sometimes it's convenient if you apply directly this one. Okay, because this one is general. This one includes this one, because we derive this directly by applying this one to this to the specific case in which f of x was equal to x. But now, okay, I stop to talk. I mean, and now we do the exercises. So compute the derivative of x to the power 3. Guys, what is convenient to use? Well, you see that in this case we have x to the power alpha, where alpha is equal to 3. So instead of using the general formula, which can be used, we can use directly the special one. So the rule tells you alpha, so 3 times x to the power alpha minus 1. But alpha is 3 minus 1, so 3x squared. So this is what we called f prime of x. So you see that it is a function. This is the function describing the slope of the tangent line to the graph of x to the power 3 as a function of x. Okay, then if you want to compute this derivative, I don't know, at the point 1, at the point x equal to 1, you get 3. 3, for example, is the slope of the tangent line to the graph of the function of x to the power 3 at the point x0 equal to 1. Okay, no, but we will do later exercises on the tangent, etc. For the moment, we want to make practice with or review better derivatives. Derivative of minus x. Remember, I told you that the multiplicative constant, if you have derivative of k times f of x, you have to copy the multiplicative constant k. Which is the multiplicative constant? Minus x is like minus 1 times x. So I copied minus 1, which is the multiplicative constant, times which is the derivative of x? Is 1. So I added it, but okay, only for the first example, guys. Equal to minus 1. So the derivative of minus x is equal to minus 1. And this is obvious because minus x is the bisetrix of the y equal to minus x is the bisetrix, guys, of the second and fourth quadrant. And its slope is minus 1. Now we have derivative of 1 over 2x plus 2. So we have a derivative. Since we need to derive all the sum, I needed to put them inside parentheses. So the derivative of a sum, I told you, in general, is the sum of the derivative. So first you have to derive this one, and then plus the derivative of this one, which is the derivative of 1 over x. Since you are at the beginning, I repeat, 1 over x is a multiplicative constant because it multiplies x. So copy 1 over x, 1 over 2, times, which is the derivative of x? 1. So 1 over 2 times 1, plus what? Derivative of 2. 2 is a constant, which is the derivative of an additive constant, is 0. So the derivative is 1 over 2. But again, this is easy, the intuition. Why? Because what it is, which is the meaning of y equal to 1 over 2x plus 2? Is a straight line with slope 1 over 2 and intercept 2. So if you compute the derivative of a straight line, I mean, the tangent line to a straight line is the straight line itself. So the slope of the tangent line is the slope of the straight line. So it's 1 over 2 because it's constant for the straight line. Okay, the intuitive explanation. Another derivative, the derivative of this sum. Again, the derivative of a sum is the sum of the derivatives. So first of all, you have to compute the derivative of this one. So copy in your mind 1 over 7. Then, which is the derivative of x to the power 3? The derivative of x to the power 3, remember the rule is alpha, therefore 3 times x to the power alpha, therefore 3 minus 1. So the derivative of x to the power 3 is 3x squared, but we have a multiplicative constant in front of x to the power 3, so 3 over 7x squared. Plus, here you have the derivative of multiplicative constant that multiplies x squared. Copy in your brain the multiplicative constant, 2 times what? So you have plus 2 times what? The derivative of x squared. But x squared is, again, a function that can be derived by following this immediate rule, which is the derivative of x squared. If you have a square here, the derivative is 2 times x to the power 2 minus 1, so 2 times x to the power 1, which is 2x. So you have 2, guys, this multiplicative constant, 2 times 2x, so plus 4x. Then you have minus the derivative of 12. Which is the derivative of 12? 12 is a constant, so minus 0. So this is the derivative function of this function. Okay, so you see that in general the derivative is a function. A derivative is a degenerate function, so only a constant, I mean only in case you have a straight line to derive. Yes, here, guys, I probably, sorry for these colors, but I probably, when I used this file for the first time last year, because before COVID, I was used to do everything on the note, on the blackboard. So maybe I saved the changes last year. So for this reason, sometimes you see something already colored. So derivative of square root of x. Oh, this is a new rule. How can I apply it? No, it's not a new rule. It's not a new rule. Apparently, if you keep this in this way, you are not able to derive it. And one can say, no, I know the formula. No, it's not. You don't need the formula of square root of x. Why? Well, you can transform this irrational function into a power function. We studied yesterday power function, remember, in the irrational function. How can you rewrite it? As x to the power 1 over 2. So observe, I still have to make the derivative, so I have to report the sign of the derivative. So here I simply rewrote the function as a power function, but in an equivalent way. Now, are you able now to compute the derivative with the instrument I provided? We reviewed together? Yes, because written in this way, which kind of function is this one? X to the power alpha. And you know that the derivative of x to the power alpha is alpha 1 over 2 times x to the power alpha minus 1. So then 1 over 2x, if you do the common denominator, you have 2 in the denominator, and in the numerator you have 1 minus 2, so minus 1 over 2. Then play again with me with the property we reviewed yesterday about powers. Because at the end, I want that you are able to rewrite. I mean, the derivative is finished technically, but if you want, you can stop here. But to make practice, we want, since we started from the derivative of a function written as an irrational function, I want you to write also the result as an irrational function. Also, okay, if we can. So 1 over 2. And how can you rewrite x to the power minus 1 over 2? You can change the sign of the exponent, but if you change the sign of the exponent, you put x in the denominator raised to the power 1 over 2. Okay, remember that x to the power minus 1 over 2, okay, can be written as 1 over x to the power 1 over 2, which means that 1 to the power 1 over 2 is 1, so x to the power 1 over 2. But x to the power 1 over 2 is square root of x. So we have 1 over 2 square root of x. So this is the derivative. So you don't need to know specific differentiation rule in general for irrational function. You transform always an irrational function into a sort of power function, okay, like we did here. So you see, for the moment, we solved the derivative simply applying these derivatives simply by applying the special formula. Look at this one. Can we apply the special formula? Well, no, because in this case, we have to compute the derivative of a function of another function. Okay, so we need to use, as I told you guys, stop a moment. If we wanted, we could have computed this derivative, this one, this one, this one, and this one by using the general rule. But there was no reason because we know also this rule and this rule is faster. But I told you, you can apply this rule only special cases. Instead, this rule is general. And now, in the example we're going to do, you cannot apply this rule, but you need the general one. So you have alpha times f of x to the power alpha minus 1 times f prime of x, the inner derivative, the derivative of the inner function. So first, you remember alpha, so 2, f of x, x plus 1, to the power alpha minus 1. So if you want to write 2 minus 1 here, which is 1, okay, so you can omit it, times what? F prime. F prime is the derivative of the inner function, which is the derivative of x, 1, which is the derivative of 1, 0, so times 1. So you can delete it, 2x plus 1. Now, look at the one below. You have the derivative of this function. You see, this function, again, is f of x to the power alpha. You have to apply the general rule. F of x to the power alpha. The derivative is alpha, so copy 5, times f of x as it is, raised to the power alpha minus 1, so 4, times what? Parenthesis, the derivative of this function, f prime of x, which is the derivative of x to the power 3. Remember, 3 times x to the power 2. And then you have minus what? Keep in your mind 2, guys. Minus 2 times the derivative of x to the power 1 over 2. Since I don't want to repeat all the steps we did above, you see that we find out the derivative of x to the power 1 over 2 is 1 over square root of 2 times square root of x, okay? But here you have minus 2 times the derivative of this function, so minus 2 multiplicative constant times this one. You see, guys, minus 2 times this one, you see that you can simplify the 2 with the 2, so you have minus 1 over square root of x, as we wrote here. Guys, when you have troubles, turn on your microphone, okay, and let me know, okay? Now, another example. Compute the derivative of this function. What kind of function is this one? Is f of x raised to the power alpha. This is the inner function, and the raising to the power 2 is the function g, the outer function. So remember, we need to do alpha times f of x as it is, raised to the power alpha minus 1, so 1, so you can omit to write it, times what? The derivative of the inner function. Copy in your mind 3, which is because it's a multiplicative constant and you have to write it. Times what? The derivative of x to the power 5, but now you should be able to understand that the derivative is 5 times x to the power 4. So 3 times 5 times x to the power 4 is 15x to the power 4. Minus the derivative of 3 is 0, so you can really omit, you can really avoid to write these parentheses because it's completely useless. And now do the computation. Don't do the product because these are stupid things. You can multiply the constant, okay, so 2 times 15, but in an exam, never multiply. When you are here, guys, never multiply, because if you multiply, you create confusion, you complicate your situation, because as you will see with me, very often when you compute the derivative, then you have to set equal to 0. Okay, don't copy, don't write. You have to set equal to 0. Are you able to solve this equation? For sure, if you make a product, you are no longer able to solve it. A product is null if either this factor is null or this factor is null. But go to the simplest one. Suppose you are in this case. You don't do the multiplication because this is a very simple equation. If you have, for example, to set it equal to 0, don't copy, because if you write it and then you read, you are doing something wrong because it's not required. I'm simply telling you, if someone asks you to find the point that makes the derivative equal to 0, you have to set the derivative equal to 0. And what you get? An equation. And if you do the product, you complicate your life. Instead, a product is null if the first factor is null or the second one is null. So you can split this equation in two. So never do when you have something already factorized. Factorized means that is a product of factor equal to 0. Never do the product. Never do the product. Otherwise, you complicate yourself. I don't know how many students, especially students who did commercial schools, when I have my courses of mathematics in the bachelor, I repeat these things so many times, and every time, especially students for commercial school, when they compute, they compute the derivative, at the end they make all the product, and then what they do? They need to decompose again everything, and they try to use Ruffini, complicated rule, and very often they are no longer able to do it. Now, sometimes they do it, but I say, okay, you did it correctly, so I evaluate correctly the exercise, but you did stupid things because you had already everything decomposed, factorized. Why did you make the product and then you decompose again, trying to be back to this form, because this is the purpose, for example, of Ruffini rule or other decomposition rule. Okay, stop. That being said, we go back to our exercises. Now we are going to apply this rule, guys, these rules, which were rule B, BS, special, etc., to compute the derivative of the following function. Then, don't look at these signs, they start automatically sometimes. I did nothing. Okay, I don't even do. Okay. Okay, so suppose you have to compute the derivative of e to the power 2x. Look above with me, which, I mean, in general, you can always apply this rule. This rule is the most general and can be applied for all these cases that follows. But suppose you want to be smartest and smart and faster. Well, which is the most convenient to use? Am I right if I'm saying that we need to use this one? I am wrong. You cannot use this one, because what kind of function is this one? Look at this function. To understand which of these one is the most convenient to use, you have to look at the function you have. You have e to the power 2x, but e to the power 2x is equivalent to, say, e to the power f of x, where f of x is 2x. So which is the most convenient to use? I told you, this one can be applied always. This cannot be applied. This cannot be applied. But the most convenient to use, if you don't want to use the general, is this one, because here you have derivative of e to the power f of x. The derivative of e to the power f of x is e to the power f of x. So this means copy the function as it is, times what? Look, f prime of x. F prime of x is the derivative of the exponent, which is the derivative of 2x, guys. 2 is a multiplicative constant. Copy it, the derivative of x is 1, so simply 2. Well, put in order 2 e to the power 2x. This is the derivative, so you see we applied this one. Derivative of e to the power 3x plus 1. Obviously, you can always apply the first one, but you cannot apply this one, you cannot apply this one, but you can apply still this one, because you have e to the power f of x. So again, you can apply directly this one. And the derivative is e to the power f of x, which means, guys, e to the power f of x means copy your function as it is, times what? F prime of x, which means compute the derivative of the exponent, which is the derivative of 3x, guys. Now we should, guys, 3 times 1, so 3. The derivative of 1 is 0, so times 3. So put in order, you have 3 times e to the power 3x plus 1. Derivative of a raised to the power 2, exponential with basis a of x squared. So which rule can we apply? Can we apply this one? No, because here the basis is e. Can we apply this one? No, this is too special, is e, and okay. Can we apply this one? Yeah, you see, a to the power x. No, because this is too special. So in this case, you need to use really the general one, because which kind of function is a to the power x squared? Is a to the power f of x. So it's this one. And the rule tells you, copy the function. So e to the power x squared times f prime of x, which is the derivative of the exponent. Which is the derivative of x squared, guys? Is x to the power alpha. So it's 2 times x to the power alpha minus 1. So x to the power 2 minus 1. So I repeat, 2 times x. Did we finish? No, because in this case the basis is a and not e. So you have also this constant to take it to this term, which is ln of a, is the logarithm with basis e of who? Of the basis of the exponential. So times ln of the basis is a, so ln of a. Derivative of this function, which is the derivative of 1 over 2 raised to the power 5 times x to the power 3, which is the rule you need to apply, guys. Can you apply this one? No. Can you apply this one? No, because the basis is 1 over 2. So can you apply this one? No, the basis, okay, is 1 over 2, but here you have x only as exponent. Here you have 5x to the power 3, so you have f of x more general than simply x. So you need to apply again the general rule. So again, the general rule tells you a to the power f of x times f prime of x times ln of a. So do with me. A to the power f of x means copy the function as it is, times f prime of x. F prime of x is the derivative of the exponent. Now, tell me if you have troubles. Can I do directly 3 alpha times the constant, which is 15, raised times x raised to the power 3 minus 1 is 2. So 15x squared. But the basis is 1 over 2. So we are in this case, as I told you, we need to consider also ln of the basis times ln of 1 over 2. Okay? Now, derivative of this one, 2 to the power 4x squared plus x. Again, which is the rule you need to apply, guys? Here 2 is like a, and the exponent is f of x. So obviously we need to apply again the most general formula. So the rule tells you multiply by e to the power a to the power f of x. So I copied it as it was. Times what? The derivative of the exponent. Which is the derivative of the exponent? 2 times 8, 4 is 8, 8 times x, because x decreases by 1 degree, so 8 times x, plus, which is the derivative of x? 1, so plus 1. Then remember, you have to multiply by the natural logarithm of a, so ln of 2 times ln of 2. So if you don't know the derivative, because for example you studied, I don't know, political sciences, and maybe you didn't do then that, and maybe you didn't study, you never studied derivative before the university, it's not a problem because they are very mechanical. So they require only practice, a lot of practice. After having done a lot of practice, they become really easy because they are very mechanical. I mean, if this is the first time you are looking derivative, okay, you say, oh, my head is imploding. Don't be scared. You need only to make exercises, to make practice, but then they are very, very mechanical. People, I think a lot of you is already very good in doing derivatives, and those people know that computing derivative probably is one of the simplest things of mathematics, because you don't need to use some logic, you have simply to apply mathematical, mathematical, but I want to say automatic mechanical rules, okay? Now, compute the derivative of this function. Which kind of function is this one, guys? Here the basis is e to the power f of x. So you can either use the most general rule, because it works always in these cases, or we can directly use the specific one. Which is the difference between the most general and the specific one? Is that when you have the basis e, you should have ln of e, which is 1, so you can omit this term. So you have simply to compute e to the power f of x, that is, copy the function, times the derivative of the exponent. So you see, I copied it, times, which is the derivative of the exponent? So 7, if you don't hate me, I say alpha times 7 is 2 times 7, 14. This the degrees of x decreases 1 by 1, so we have 14x. Then we have minus 1 over 2 times x to the power 3. The derivative of x to the power 3 is 3x squared, so minus 3 over 2 x squared, plus the derivative of 1 is 0. You can omit it. Again, guys, if you have troubles, turn on your microphone and talk, okay? Now, the third and last case, the formulas C are reported, use the following elementary rules, the one involving the logarithms with general basis and with specific basis, and both the composite function case and this very special. Okay, here I wrote it last year for students. Don't be scared. I simply told you that if you write f prime of x over f of x is like writing 1 over f of x times f prime of x, because in my mind, I always do the computation by following this reasoning, because I say 1 over the argument times the derivative of the argument. Okay, so I think I always done this. I mean, it's the same, okay, guys, it's the same. Because if you do the product, I mean, you write it directly here, but I prefer to write separately. So for this reason, we are going to, now we go on. So derivative of 2 times ln of x. Which rule can you apply, guys? Remember, this is the derivative of a constant times f of x. So general rule tells you, copy the multiplicative constant, 2, and multiplies by the derivative of f of x. But the derivative of f of x is ln of x. Is there a rule that we can apply immediately? Yes, because we know that the derivative of the logarithm with basis e of x is 1 over x. So 2 times 1 over x. And then I wrote 2 over x, okay? So derivative of 2 ln of x squared. Can we do the derivative? Yes, we have a multiplicative constant, so the multiplicative constant must be copied. Which kind of rule can we apply? Guys, this is ln of f of x. You see ln, so we can apply directly this one, which is the easiest one. Okay, you can apply also the one above, but you can apply directly this one. So as I told you here, the explanation I did, 1 over f of x times f prime. So which is 1 over, which is f of x, is the argument of the logarithm. So x squared times what? F prime. Which is f prime? The derivative of the argument, which is the derivative of x squared, is x to the power alpha. Is simply 2 times x to the power 1, so 2x. Then do the multiplication, 2 times 2 is 4, and simplify the x with the square, and what you get is 4 over x. Derivative of the natural logarithm, ln is also called natural logarithm, of x to the power 3 plus x squared. Which kind of derivative rule we need to use? When we can either use the longest one, I mean the most general, or this one. You cannot use obviously this one nor this one. So we use this one. So 1 over f of x, 1 over f of x, 1 over the argument of the logarithm. So x to the power 3 plus x squared. Times what? F prime of x, the derivative of the inner function, that is the derivative in this case of the argument of the logarithm. So which is the derivative of this one? Well, this is a sum. The derivative of the first, derivative of x to the power 3, I think we computed it already 6 or 7 times. So it's 3x squared plus the derivative of x squared, which is 2x. Remember, the parenthesis is important. Okay, can we simplify a little bit this expression? Yes. Why? For example, you see that in the numerator, okay, we have 3x squared plus 2x. You see that you can collect x. So if you collect x, you have x times, okay, I wrote it here, 3x plus 2. You can collect also x or x squared in the denominator. I simply collected x to simplify it. If you collect x, you have x squared, that multiplies x squared plus x. Simplify this with this. Obviously, guys, this is the result. Obviously, if you want, you can even write 3x plus 2 over, collect again x times x plus 1, but you can stop here. But if you want, no, it's still correct, okay? If you want to further decompose this and factorize it into the product between x and x plus 1. Logarithm with basis 2 of x to the power 3. This logarithm with basis a of f of x. So we cannot use this one, we cannot use this one, we cannot use this one. In this case, we need to use the most general. So again, is 1 over f of x times f prime times logarithm with basis a of e. So we go below, okay. So as I told you, 1 over f of x, that is 1 over x to the power 3, times what? The derivative of the argument, which is 3x squared, so times 3x squared, times what? Logarithm with basis a, so in this case, the base is 2, logarithm with basis 2 of e. Simplify what you can. So you see, I simplified the x squared with the 3, so you still have with this, with this exponent. So you have 1 over x times 3 logarithm of 2 with basis 2 of e. Okay, and I wrote it in this way. Okay, 3 over x logarithm with basis 2 of e. Derivative of logarithm with basis 1 over 3 of x to the power 4 plus 2x. Which rule do we need to use? This logarithm with basis a of f of x. So we need to use the general rule. Again, 1 over f of x, so 1 over the argument, times f prime of x. F prime of x is the derivative of the inner function. So 4x to the power 3 plus the derivative of 2x, guys, is simply 2. But remember, the basis is 1 over 3, so we need to multiply also by the logarithm with basis 1 over 3 of e. Okay, stop here because you cannot simplify this one. There is nothing to collect. Okay, so until now, we applied the elementary rule, of the different function. Now we are going to use together, to mix together all the elementary rules. So in this case, you have to think which rule you need to use, and you have to think also to the general rules if it is necessary. So derivative of 2 raised to the power 2x plus x to the power 3 plus 2 ln of e. So guys, this is the derivative of the sum, and the general rules tells you that you need to compute the sum of the derivatives. So derive this one plus the derivative of this one and plus the derivative of this one. But to compute the derivative of this one, you have to think to the specific rule we studied. Which kind of function is this one? Is an exponential function. In particular, is a function of the type, which is the basis 2. So basis a, the exponent is f of x. So this is, guys, a function of the type a, where a is 2, to the power f of x. We applied the rule before. Remember, the derivative of a to the power f of x is a to the power f of x first. I copied it. Times what? F prime of x, which is the derivative of the exponent, which is the derivative of the exponent of 2x, is 2 times 2. Times what? Ln of the basis of the exponential, so ln of 2. So this is the derivative of the first term, plus, again, the derivative of x to the power 3. Which kind of function is this one? X to the power alpha. So the derivative is alpha 3 times x to the power alpha minus 1. 3 minus 1, 2. Plus what? Oh, did I do a mistake? No. Why? Here was only a trick. Stupid trick, because, guys, ln of e obviously is equal to 1. However, ln of e is a number. 2 is a number. A product of two numbers is a constant, a number. So the derivative of a number is 0 plus 0. So it's even awful this, because I should have written logarithm of something else. Okay. No, it's good. Okay, correct. To make a trick, this is a stupid trick at all. So here, let me see. Can we do something? Can we collect something? Well, you can keep the derivative either in this way, or look, apply the property of the powers. We studied them yesterday. You see that here you have 2 to the power 2x times 2. You have a product of two powers with the same basis. So to make a little bit better the derivative, I mean, in a better form, you can do the product. 2 times 2, I mean, is a product of two powers with the same basis. The result is a power with the same basis and the exponent alpha plus beta. So 2x plus 1. I said alpha plus beta because yesterday we used this notation. Remember, 2 to the power alpha times 2 to the power beta is 2 to the power alpha plus beta. So I simply did this one. Another can say, I don't like this form. I want to put the 2 inside the logarithm. You can. You can even write, guys, if you want, the result as 2. This is a 2. 2 to the power 2x times ln of, ln of 4, for example, plus 3x squared. Why? It's still correct. Why? Because instead of doing the operation I did here, you can even multiply the 2 by ln of 2. This means, remember the property of the logarithm, the multiplicative constant can be written as the exponent of the argument of the logarithm. So this can be written as ln of 2 squared. Okay, but 2 squared is 4. Okay, do another derivative now. Look at this derivative, derivative of 1 plus ln of x to the power 2. Which kind of function is this one? Well, look at this one. You have something raised to the power 2. So you have f of x to the power 2. So this is the derivative of f of x to the power alpha. So we apply the first general rule. The first rule I have shown. The first rule I have shown you. So, which is the derivative of f of x to the power alpha? Is alpha times f of x to the power alpha minus 1, 2 minus 1. So I can omit to report the exponent, times what? The derivative of f of x. The derivative of 1 is 0. Which is the derivative of ln of x? Rule number C, special, super special case, is 1 over x. So this is the derivative, and you don't have to do the product. I mean, if you want, you can even make longer this. No, it's okay this way. You don't have. You have to do nothing. Okay. Look at the next derivative. Derivative of 1 plus e to the power 3x, everything raised to the power 4. Which kind of function is this one? Because this is fundamental. You have to understand which kind of rule you need to apply. And as I told you, if you do not know yet the derivative, first you should have next to you the table I prepared, which was at page 10. I do not remember 11. I do not remember. Keep next to you at the beginning the table, and then try to find by looking at the table which is the rule you need to apply, and then follow the rule. Then at a certain point you have to do them automatically. So what kind of function is this one? Well, you have a parenthesis raised to the power 4. So this means that we have the derivative of f of x to the power alpha. So we need to apply the general rule we have applied in the previous example. Remember, derivative of f of x to the power alpha is alpha times f of x, copy it, raised to the power alpha minus 1, 4 minus 1, which is 3, times what? F prime of x, that is the derivative of the inner function. But here you have a sum, which is the derivative of 1, 0, plus the derivative of e to the power 3x. But e to the power 3x is is one of the 4 rules belonging to case B. This is, which kind of function is e to the power 3x? Is e to the power f of x. Which is the derivative of e to the power f of x? Is e to the power f of x. So you see, I copied it here, e to the power 3x, times what? F prime of x, which is the derivative of the exponent, which is the derivative of 3x, is 3. Then obviously you can delete the parentheses, the 0, and the only thing you have to multiply is 4 and 3, so 12 e to the power x to the power 3 times this. Do not develop the cube because it does not make any sense. Okay, complicates only the life. Now, look at this function, derivative of e to the power ln of x plus 2x. Which kind of function is this one? You have e raised to the power f of x. So we are again in case B, in particular this was called BS, okay. This is the derivative of e to the power f of x. Which is the derivative of e to the power f of x? Is e to the power f of x times f prime of x, where f prime of x is the derivative of the exponent. The exponent is this one, is a sum. You have to compute the derivative of the first, which is the derivative of ln of x. Is the very special case C, is 1 over x, plus the derivative of 2x, which is 2. You can either stop here, guys, or if you want, see what I did, because I simplified a little bit this expression. Because, guys, you see e to the power ln of x plus 2x can be seen as e to the power alpha plus beta. This is alpha and this is beta. And you know that e to the power alpha plus beta can be seen as the result of e to the power alpha times e to the power beta. So what I'm saying is that we can decompose it as e to the power ln of x times e to the power 2x. Then I copied it. Here, if you want, you can do also the common denominator, but we will see. Maybe I did it later, okay. Now, why I wrote this in this way? E to the power ln of x, guys, property of the logarithm, which is e to the power logarithm with basis e of x. We did it so many times also this morning. Is x. E to the power ln of x is equal to x. To be precise, guys, why I ask you a question? Okay, we solve it, then I ask you a question, but I answer to the question. I ask you, but I answer, but only to think, so you answer in your mind. Okay, so x times e to the power 2x, then I made the common denominator. So make the common denominator, because in the denominator you would have x, and in the numerator 1 plus 2x. Then you can simplify x with the x in the denominator. So for this reason here I reported e to the power 2x times 1 plus 2x. Guys, okay, this is the derivative. A question that is not related to derivative. If I ask you, suppose I ask you, I told you that e to the power ln of x is equal to x. So I'm asking you, so y equal to e to the power ln of x is equal to x, therefore this function is equal to the function y equal to x. Which is the graph of the function y equal to x, guys? Is the bisectrix of the first and the third quadrant. So this is a graph of y equal to x. So if I ask you, plot the graph of y to the power, y equals, e to the power ln of x, you write, come mai qui non scrive? Oh, why? Okay. Am I right? Am I right? Because this is equal to x. Am I right? So what I'm saying is that I'm asking you, is the graph of y equal to e to the power ln of x, since this is equal to x, equal to the graph of y equal to x. We have y equal to x, y equal to x. The answer should be obviously no. No. Why? Because there is a difference, guys. This is the graph of y equal to x. If you want to plot y equal to e to the power ln of x, you can do this step, the one I reported. Yes, perfect. However, which is the domain of the logarithm? X greater than 0. So here, x greater than 0 you have. So the graph of e to the power ln of x is this one, but to be more precise, remember, x must be strictly greater than 0. So here you have an empty circle, because empty circle means that the function is not defined for x equal to 0. So the function is, the graph is simply this one, which is equal to this part of the graph of y equal to x. So you see, we apply the property, we got x, but remember, x must be strictly positive. So the function y equal to e to the power ln of x is not perfectly equal to the graph of y equal to x. Okay? We say, guys, only to talk, we say that this function is a restriction of this one. Restriction means that along the same domain they are equal, but this one has a domain restricted compared to the previous one. Because you see, this is defined everywhere, the straight line. This one instead is defined only for x strictly greater than 0. So this function is a restriction of this one, because the domain of this one is completely contained in this one. But this one has a restricted domain. No, it was only an observation, guys. Okay, only an observation. This has nothing to do with derivative, okay? It was only an observation. Okay, wait a little bit. We go a little bit on, but then let me see. We do other derivatives. Okay, guys, suppose you have to derive this function. 3 to the power 1 over 5x plus ln of 3x. Ignore this a, probably this is linked to an explanation of last year. What I'm saying, in reality, if you want, you can cancel it, okay? Because if you go on, now here I don't know, but if you have a PDF, if you open a PDF here, I don't know how to do it, but if you open with, open it with Acrobat Reader, not with the file I used here, you can delete then this, because this has been written with color using directly Adobe Reader, Acrobat, and so you can delete them if you want, if they create to you problems. So now probably I wrote it to denote to remember the student that this was a derivative of which function? 3 is like a to the power alpha, so probably I wrote it to denote that this was a to the power, not alpha, sorry, a to the power f of x, which is the derivative of a to the power f of x. Remember, is first of all a to the power f of x, so copy it. Then you have to multiply by f prime of x, which is the derivative of the exponent. The exponent is a sum, which is the derivative of this. Okay, I mean, you have a constant times x, so you have simply 1 over 5, plus, which is the derivative of ln of 3x. ln of 3x is a function of the type ln of f of x. The derivative of ln of f of x is 1 over f of x times what? The derivative of the argument, that is the derivative of 3x, which is 3. Then you can simplify 3 with 3, close parentheses, times, remember, you have to multiply by ln, sorry, ln, ln of the basis, so ln of 3. You can stop here. If you want, you can make only the common denominator here, but who cares? Okay, we do not care now. We want to do only derivatives. Okay, so you see, you must be flexible in the sense that you need to learn the rule of differentiation, because to complete this derivative, you see, I applied first the derivative of a to the power f of x. Then I needed to apply the derivative of a sum, and the derivative of a sum is the sum of the derivative of this one. The derivative of this one involves the derivative of a product of a constant with the function, and in particular, of a constant times x to the power alpha, plus the derivative of this one involves the application, the knowledge of the derivative of logarithm of f of x. But after having studied the rule and do the exercise and repeat, you have so many exercises at the end with all the steps and solutions, so you can make practice when you want. Okay, so go to this one. Derivative of this is the first type. We are going to see a derivative like this. Because you see, you have e to the power 2x times x squared plus 1. So what kind of derivative function is, first of all? Is a product of two functions. So this is the first time I provided the general rule, but it is the first time you are going to do with me the derivative of a product of two functions. So for example, call this function, the first function f of x, call the second function g of x. I use notation f and g to be faster. And remember, I repeat with you the rule. The rule tells you have compute the derivative of f, so f prime times g as it is first. So f prime, so this is f prime. Which is f prime? The derivative of e to the power 2x. But e to the power 2x is a function of the type e to the power f of x. The derivative of e to the power f of x is e to the power f of x times what? F prime of x, which is the derivative of the exponent. The derivative of 2x is 2. Times what? G as it is. So this is g. And the rule of the product tells you that you have to do then plus f, so copy f, so e to the power 2x, times what? The derivative of the second function, so times g prime. G prime is the derivative of this one, which is the derivative of x squared, 2x. The derivative of 1 is 0, so simply multiply by 2x. Now here, guys, instead of keeping everything in this way, you see that you have the sum of these two terms. Do these two terms share something in common? Yes, they have in common e to the power 2x. And also the 2, see, 2 here and 2 here. So it's better to collect 2 e to the power 2x. So if you collect 2 e to the power 2x, here you have x squared plus 1. Plus, you collected this, so plus x. Okay, this is useful. Well, it's always a problem. It's stupid if you have a solution like this and you do the product. It is always instead a good thing, if you can, to express your derivative as a product of function. If your exercise consists only in solving, okay, like we do now it's not important. But for solving an exercise, as I told you before, suppose you need to set the derivative equal to 0, then you need to solve an equation. If you solve this equation by making the product, you are not able to solve it. On the contrary, if you factorize it, it's easy because the product is null if either the first factor is null or if the second one is null. Okay, stop. We do another. We do the next two examples and then we do the break. Okay, so we stop here. Then we do 15 minutes of break. So derivative of e to the power x times ln of x. Again, this is the derivative of a product. So you need to apply the general rule of the product. So the general rule tells you that you have to do what? F prime times what? Times g as it is. So which is f prime, guys? Troubles. The derivative of the exponential of x. But this is a very special case, super special. The derivative of e to the power x, if you look the rule, is e to the power x times g as it is. So copy the logarithm. Plus what? The rule. This is always the same rule. Plus f. F is the first function. So which is the first function, guys? In the product is e to the power x. So times e to the plus e to the power x times what? G prime. G prime is the derivative of the logarithm of x, of ln of x, which is a very super special case also, which is 1 over x. Again, can you factorize this result? Yes. That is, can you decompose it? Yes, you can collect e to the power x, and you can write e to the power x times parentheses ln of x plus 1 over x. It's not necessary that you do the common denominator, at least at the moment. Okay. As I told you, we are going to do the last one, and then we do the break, this one. Okay, let me cancel something. Can I cancel? Oh, I can cancel also. Oh, no, I can cancel everything. Oh, very good. Oh, beautiful. No, okay, who cares? Now, this is a derivative of the ratio. I suggest you to call the numerator as f and the denominator as g. So I mean f of x and g of x. This is to compute the derivative of this function, we need to use the general rule, which is the derivative of a ratio. The derivative of a ratio tells you that in the denominator you need g squared, that is g of x to the power 2. Which is g? Is the denominator. X squared raised to the power 2 is a power of power, so x to the power 4. Then you have to do in the numerator f prime times g, let me write everything, minus f times, non riesco a scrivere, f times g prime. I repeat, you have the formula, okay? So f prime is the derivative of f, is the derivative of the numerator. Which is the derivative of the numerator? Look, I did all the step really. 1 plus 0, derivative of x is 1, derivative of 1 is 0. Times, the rule tells you, multiply by the denominator as it is. The denominator is g, x squared. Minus, parentheses, the numerator as it is, put it inside parentheses, guys, because otherwise you commit a mistake if you don't put x plus 1 inside parentheses, because then you have to multiply x plus 1 by what? The derivative of the denominator, which is the derivative of x squared, is 2x. Then you can make the computation, x squared minus 2x squared minus 2x. Simplify, I mean, sum this with this. You have minus x squared minus 2x. And guys, if you want to do an additional step, you see, you can collect, for example, minus x, or as I did here, you can collect x in the numerator. Numerator, you collect x and you get x times minus x minus 2 divided x to the power 4. Okay, then you can simplify x with the 4 and put it here 3. And for this region, you get minus x minus 2 over x to the power 3. Okay, as I told you now, we do a break. Let me see. 15:23, we assume that there are 25 minutes past 15. So at you will be back at 20 minutes to 4 to 4 p.m. Okay. Okay, guys. So 18 minutes of break.
Okay.
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 Okay, thank you.
Okay, bye.
Thank you.
Thank you. Thank you, guys.
Okay,
Thank you, guys. Thank you, guys. If you have questions to ask, you can ask me. Okay, guys. Now, still a minute or 30 seconds, I don't know. I share again my desktop. Mamma mia. So, guys. Qual è questo? No, ok. I'm not going to do this one. Here, okay. Okay, guys. We continue with the lecture. As always, I let you go at a quarter. Well, we still work for another hour, okay? No, don't believe me. We will see, okay? We will see, because if I finish, I'm happy. Otherwise, if I need 2 or more minutes, you know that I continue. So I hope to be able to finish what I want in an hour or less. Not less. So we continue, guys. So, okay, look at this function now. Suppose you want to compute the derivative of 1 over x squared minus 4. What kind of function is this one? It is a rational function. So this can be seen, no, it can be seen. This is a ratio, okay? How can we derive it? Okay, one can derive it in another way, but how can we derive it? Sorry, how can we derive it? Well, you need to take, remember, f is the numerator and g the denominator. So first of all, the derivative is a fraction in which in the denominator you have g raised to the power 2. So x squared minus 4, then raised to the power 2. Never develop this square in the denominator, please. It's stupid and useless and creates problem only. Then in the numerator you have the derivative of what? Of f. Which is the derivative of 1, guys? F prime. Derivative of 1 is 0. 0 times the denominator as it is, so times g, x squared minus 4, minus the numerator as it is, therefore minus 1, times what? G prime. G prime is 2x. So 0 times this, x squared minus 4 is 0. So you have minus 2x divided x squared minus 4 to the power 2. Derivative of 2x over x to the power 3. Here, guys, I computed this derivative as a ratio. Another student, if you want, there is another method. Oh, let me. Oh. Derivative of 2x over x to the power 3, I computed it as a ratio. Alternatively, I could have had computed this one as 2x times, put x in the exponent, x to the minus, in the numerator, x to the minus 3. So you have two choices. You can either compute the derivative of a ratio like this, or transform this ratio into a product by multiplying 2x by x to the minus 3. And in this case, you can apply the rule of the product. Here, however, I applied the ratio rule, so we see the ratio. Again, remember that the numerator is f, the denominator is g. First of all, g squared. G squared is the denominator to the power 2. So is x to the power 3, then raised to the power 2. And remember, this is a power of power, so the result is x to the power 3 times 2, which is 6. I reported it because someone is used to write x to the power 9, which is obviously wrong. It's x to the power 6. Then in the numerator you have the derivative of the function of f, which is the derivative of 2x, is a function of the type a to the power x. This is a special rule. Is a to the power x, therefore 2x, times what? ln of 2 times what? The denominator as it is, x to the power 3, minus the numerator as it is, 2x to the power x, times what? The derivative of the denominator, which is 3 times x squared. Okay, can we rearrange a little bit? Look at the numerator. Can we collect something? Well, you see, you have 2x here and 2x here. You can collect also x squared. So you can collect 2x times x squared. So 2x times x squared. Then here you have x times ln of 2. So x times ln of 2. And here you have minus only 3, minus 3. Can we simplify something? Yes, we can simplify this with this one. And here you have 4. So in the denominator you have x to the power 4. Okay, so you see here I simply copied. Okay, this is the derivative. This is the derivative that you should obtain if you apply the differentiation rule of the product of these two functions. Another computation, derivative of this function. Which kind of function is this one? You have a function raised to the power 4. See, so this the derivative rule of f of x to the power alpha. Derivative tells you alpha times f of x to the power alpha minus 1, so 3, times what? The derivative of the inner function, that is this one. So which is the derivative of this one? Is the derivative of a sum. Derive the first. Which is the derivative of e to the power 2x? Is the derivative of e to the power f of x. And the derivative is e to the power f of x times what? The derivative of the exponent, which is the derivative of 2x, is 2. So this one. And then you have plus what? The derivative of e to the power x. But the derivative of e to the power x is a very special, super special derivative, which is simply e to the power x itself. So plus e to the power x and plus the derivative of minus x, which is the derivative of minus x, is minus 1. So minus 1. Derivative of x to the power 3 times ln of x. What do you have here? You have a product of two functions. X to the power 3 is f, and ln of x is g. The product rule tells you that you have to compute f prime, which is the derivative of x to the power 3, 3x squared, times what? G, the second function as it is, so times ln of x, plus what? F as it is, x to the power 3 times the derivative of the logarithm of x. The derivative of the logarithm of x is elementary, a super elementary rule, which is 1 over x, so times 1 over x. Then you can simplify this with this one, and it is always good to collect something if you can. Here you see you have x squared, so collect x squared, and you get x squared times 3 ln of x plus 1. Derivative of the logarithm of 1 over x to the power 3. Here I saw that I computed the derivative in two ways, but first we follow this way. So what kind of derivative is this one, guys? Is the logarithm of f of x. Logarithm of f of x with basis e. And you know, and we know that you have to do 1 over f of x, so 1 over the argument, times what? The derivative of the argument. But which is the argument of the logarithm? Is a fraction, if you want to use it as a fraction. Okay, yeah, there are other ways, but I'll use this one here. So derivative of this function. So how can you compute this derivative? You have to take the denominator to the power 2. So x to the power 3 to the power 2, which is x to the power 6. In the numerator you have the derivative of 1, which is 0, times the denominator as it is, x to the power 3, minus the numerator, so minus 1, times the derivative of the denominator, which is 3x squared. How can you rewrite this? 1 over x to the power 3 can be written as 1 times x to the power 3 over 1. Okay, transform it into a product. So it's x to the power 3. Then here what you have, this is 0. You have minus 3x squared over x to the power 6. Since you cannot have a plus and a minus 1 next to the other when they multiply, okay, you have so to put a parenthesis. Can you do something else? Yes, you can simplify, or as I did here, first I multiplied this with this, so minus 3x to the power 5 over x to the power 6. Then you can simplify this with the 6, and you get minus 3 over x. Here I provided also an alternative way to solve this derivative. ln of 1 over x to the power 3. Again, we do it in an alternative way, where here we have the derivative of ln of f of x. But you know that you can rewrite 1 over x to the power 3 as x to the minus 3. So derivative of ln of x to the minus 3. So still here, I have still to compute the derivative, okay? So the rule tells you ln of f of x. So 1 over f of x. So f of x is x to the minus 3. Times what? The derivative of the argument. Written in this way is no longer a ratio like before, but in this case is a power. How can you compute this derivative? Is the derivative of x to the power alpha, which is alpha minus 3 times x to the power alpha minus 1. So minus 3 minus 1 minus 4. Okay, we have already seen that you can put x above by changing the sign of the exponent. So you have x to the power 3. Now you can put x to the minus 4 in the denominator by changing the sign of the exponent. So minus 3 over x to the power 4. You can simplify x to the power 3 with the 4, and you get minus 3 over x. Okay, same result. Okay, now derivative of logarithm of square root of x. What is it? It's the derivative of the logarithm of f of x. So the derivative of the logarithm of f of x is 1 over f of x times f prime. But you see that I do not remember, I mean, I remember, but suppose we do not remember, which is f of x for us? Square root of x. Suppose we do not remember the derivative of this function. We computed it previously, but suppose we do not remember. So we write derivative, again, logarithm. How can you write this as a power function? So x to the power 1 over 2. Now you have everything to apply the rule, because you have derivative of ln of f of x is 1 over f of x times f prime of x. F prime of x is the derivative of this one. Which is the derivative of this one? Is 1. Remember, x to the power alpha is alpha, so 1 over 2 times x to the power alpha, 1 over 2 minus 1. If you do the computation, 1 over 2 minus 1 is minus 1 over 2. Then let me rearrange a little bit. So this can be written as 1 over square root of x. 1 over 2. Remember that we did it already before. You can put x into the denominator, okay? So you have 1 over 2 times x to the power 1 over 2. But x to the power 1 over 2 is square root of x. Do the product. Square root of x times square root of x gives x. So you have 1 over 2x. Let me see what I did below, because I wrote alternative. Alternatively, you see, I did again the same derivative. I did the same steps. Okay, here, guys, I applied the property of logarithm. I took, remember that the exponent of the argument can be written in front of the logarithm. So derivative, so you see that I still have to compute the derivative. So until you do not compute the derivative, you have to still report the sign d. So I simply copy the exponent of the argument in front of the logarithm. Now, written in this way, you have the derivative of a constant times ln of x. Remember that the multiplicative constant must be always copied first, so 1 over 2. the derivative of the logarithm is a base and elementary rule immediate, which is 1 over x. So again, you see, you get the same result. What? Okay, cancel this because if you read here, you are confused. I did it last year, but was correct, but there was a reason. They were two different things. Okay, no, they are two different things. So if you read them, you say, what? There is no, no, I know what I did. No, what I'm saying, let me cancel, and then I explain. Now, we do this derivative only to play. This derivative is difficult, okay? So it's I teach you the principle, but guys, because now I know why I wrote this here, but cancel it because if you read it, you say what is wrong. Okay, obviously it's wrong because you don't know. I wrote them in two different moments. So I will tell you, okay, so don't ignore the green here because it was an explanation of last year saved, but it was explanation did in two different moments. Instead, since you don't know, if you read it, you read at once, and obviously it's wrong if you read it at once. What I was saying, now here we have this strange function, which is the derivative of x raised to the power x. Only to play, guys. This is complicated, I know. Not complicated, I mean, we will see. To compute this derivative, guys, there are also in some books the general rule to compute this derivative, but we do not care about rules unless with few exceptions. So we can derive it already by using the rule we know. This function, guys, has a domain x strictly positive. So this function is defined for x greater than 0, okay? Greater than 0. And in particular, guys, so we can consider rewrite the function, since this is a function that we have never seen, because this is not an exponential function a to the power f of x. It's not a power function like x to the power 3, x to the power a number. Here is a function that belongs to the more general case, f of x raised not to the power alpha, but to the g of x. So this is a very complicated, I mean, there exists a rule which is complicated. I do not remember the rule. I mean, I do not need to remember because I can get it, I can derive it. But in fact, we solve this without knowing the rule. The trick is the following. Okay, you know that I wrote this, now I'm writing exactly the same thing probably I wrote before. So remember that e to the power ln of x is equal to x. Okay, remember when x is for x positive. Okay, so if this is true, if I write e ln of people, no people, I copy this function. I would have written people e to the power ln of x to the power x. Apply the rule, the property, guys. Apply the property that we studied already. Remember, a to the power logarithm with basis a of x is equal to x. So e to the power ln of people will be equal to people, where people is x to the power x. Okay, so I simply use the property of logarithm and exponential. So since an x to the power x is strictly positive, okay, so really there is completely no problems in doing this operation. So instead of computing the derivative of x to the power x, I compute the derivative of e to the power ln of x to the power x. And one said, oh, it was already difficult, now it is even more difficult. No, because now we have all the instrument in almost a moment, not yet, in almost a moment. In almost a moment we have all the instrument we need, because we cannot compute it directly. Well, now this seems to be more difficult because you have e to the power ln of x to the power x. But apply the property of the logarithm again. X is the exponent of the argument, so you can write it here. Now everything is done, because now with the instrument we have, we are able to compute this derivative without problems. In fact, now we talk. Which kind of function is this one? Is the derivative of who? E to the power f of x. But we are able to compute the derivative of e to the power f of x. Why? Because the derivative of e to the power f of x is e to the power f of x first. So I copied it. Times what? the derivative of the exponent, which is x ln of x. I reported the sign, so you can remember better. Guys, which is, look here what I did. E to the power, guys, e to the power x ln of x is equal to e to the power ln of x to the power x, okay? Is this term. So what I'm saying, this term is equal to this one, which is equal to this one. Since I don't need to derive it, because I need to derive this term now, I need to copy it. Since this was equal to this one, which is equal to this one, instead of writing this one, I write x to the power x, okay? This is equal to this one, which is equal to this one. Now, times the derivative of what? Of this product. What is it? A product. Derivative of the first, which is the derivative of x? 1. So 1 times the second function as it is, ln of x, plus what? The first function, which is x, times the derivative of ln of x, which is the derivative of ln of x? 1 over x. Simplify, simplify, and you get this rule. Sometimes in book you find this rule, and this is, guys, the special rule, because the more advanced rule is f of x to the power g dx. So this is the special case. This belongs to the case in which both f of x and g of x are equal to x. But the general rule is the following, and if you want, we derive it to play. We derive it to play, only to play, and to make practice. Let me see, someone is writing something. Maybe, let me check, because maybe someone is asking to get inside the room. Let me see, guys, someone is asking to go inside the room, so wait, I hope. Okay, in a moment I'll be back to answer because we need time. So let me cancel here. No, I need a lot of space. Page 13, let me see if I have an empty space. A full complete, no. No, may I do it here. Maybe here I have more space. If now I show you how to get the derivative. Now let me see if I can accept her. Ha chiesto di Irene, are you here? Because I don't see. No, you are not here, Irene. Perché fa così sto coso? Quando l'ha chiesto? E vai, cavolo. Perché non si apre, ragazzi? Perché fa così sto cavolo di... Fate ritornare qua, fa vedere se... Let me see. Okay, now I can accept her. I don't know why this... Okay, team is team, okay. So, as I told you, here I'm trying to collect some space to show you how to get the derivative of f of x to the power g of x. Okay, I show you the general formula that you find in some book. The trick is the following. F of x is strictly greater than 0, and this is a function which is defined, which is strictly positive everywhere. So guys, what I wanted to tell you is that the trick is the following. We do not have a rule to derive this function. Okay, only to play, guys, only to play. So I go below, now I go here. Derivative of, the trick is the following. This can be written as the derivative of e to the power ln. If you don't hate me, guys, can I write simply f to the power g? So I can simplify the notation, only to simplify the notation, but this means f of x and this means gx. From the property of the logarithm and the exponential, e to the logarithm of Pippo is equal to Pippo, and here is Pippo, okay? So equal to the derivative of e to the power ln of f, but g is the exponent of the argument. You can write it in front of g. So you have e to the power g times okay, I'm not able to write. Let me cancel, guys, sorry. I try to write better. Derivative. Oh, I want to cancel. Okay, I write it again, guys. Derivative, I told you, of e to the power. G can be written in front of the logarithm, of g of x times ln of f. Okay, so we have to derive e to the power g of x times ln of x of f of x, ln of f of x. Are we able to compute this derivative? Yes, because this is the derivative of e to the power a function. The derivative of e to the power f of x is e to the power f of x. So guys, pay attention, is e to the power f of x. So I need to copy it, okay? But this is equal to this one, it is equal to this one. So I can simply write f to the power g times what? The derivative of f, which is the derivative of the exponent. So times the derivative, parentheses, of g of x times ln of f. Okay, which is equal to f to the power g times parentheses. Now we need to do the derivative of the product, because here you have, guys, g of x, which is a function, times ln of f of x. So which is the derivative of a product? The derivative of the first, so I denote it as g prime, times what? The second as it is, times ln of f, plus the product tells you copy the first function as it is, g of x, times what? Which is the derivative of the logarithm of f? Remember, is 1 over the argument. Cosa succede adesso? Si aprono sempre queste pagine che rompono. Sto coso qua, sorry, 1 over f times what? F prime. So I can write f prime already here, f prime of x. So this is the formula in the book you find there in some books. Derivative of f of x to the power g of x equal to f of x raised to the power g of x times parentheses g prime of x times logarithm of f of x plus g of x times f prime of x divided f of x. And the exercise we did previously was the special case. This is the general formula, but okay, you don't have obviously to know this formula. I mean, you see that I didn't know even either. I mean, I derived it, but I do not remember this formula otherwise. Okay. So we go back. We come back to simpler things. Okay, we come back to simpler things. So we did exercises related to the computation of the derivative. Now we are going to see other exercises related to derivatives. Ancora qua. Cos'è sta roba? Ah no, these are the exercises that if you want you can do for home. I told you because you have several derivatives. I did all the steps, so you can make further practice if you need it, whenever you want, even in the future, if you have no time now. Qual era dove eravamo? These are exercises for home, for home. Dove eravamo? Limit, no. Yeah, we are here. A different exercise that requires, however, the concept explained this morning. Examples: find the slope of the tangent line to the following function at the point x0 equal to 1. Remember, only to review, guys, it allows to review only the concept I explained this morning about the meaning of derivative, which is the slope of the tangent line. How can you get the slope of the tangent line to the graph of a function at a given point? First, you need to compute the derivative function, then evaluate the derivative at that point, and this provides you the slope of the tangent, that is the instantaneous growth rate at the point x0 of your function. So we need essentially to find the slope of the tangent line. So this f of x. So we need the first order derivative. Which is the derivative? Which kind of function is this one? Is e to the power f of x, whose derivative is e to the power f of x times the derivative of the exponent, which is 1. So the derivative is simply e to the power x plus 1. Now, which is the slope of the tangent to the graph of the function of this one at the point x0 equal to 1, remember, is f prime of x0. This means f prime, the derivative function, evaluated at x0, which is 1. So f prime of 1 means take 1, put it inside the values of x in the derivative. So you have e to the power 1 plus 1 is e to the power 2. Okay, so this means that the slope of the tangent line, m of the tangent line, is e squared, or in other terms, the instantaneous growth rate of the function is e squared. Only to talk, guys. What does it mean that the instantaneous growth rate at the point x equal to 1 is x squared, e squared? It means that the estimated change in the value of the function as you pass from x0 to x0 plus 1, so from 1 to 2, as you increase the value of x of 1 unit starting from x0 equal to 1, the expected increment in the value of the function is e to the power 2, which is about 9. It's smaller than 9 because it's 2.7. Okay, to the power 2, it would be, I don't know, about 7, something or 8, something like this. Okay, so is the instantaneous growth rate, that is the estimated change in the value of the function starting from x0 if you increase x of 1 unit. What I told you this morning. So in this case, increasing x of 1 unit means that you pass from 1 to 2. So if you increase x from 1 to 2, you expect an increment in the value of the function equal to e squared. So huge increment, a huge increment. Obviously, guys, this is only an estimated increment. Remember, if you move along the tangent line and not along the true function. Remember all the graph we saw this morning. Okay, repeat the exercise for f of x equal to ln of x to the power 3. We want to find the slope of the tangent line to the graph of this function, again at the point x0 equal to 1. What do you need to do? You have simply to compute the first order derivative at the point. So if I ask you, evaluate the instantaneous growth rate at the point x0 equal to 1, you have to do exactly the same computation you need to do to compute this, to get the slope, because they are the same thing. So first order derivative, what kind of function is this one? Ln of f of x. The derivative rule of the logarithm tells you 1 over f of x times f prime. F prime is the derivative of x to the power 3. That it is, I think we did it today already 14 times, I don't know, 3x squared. Simplify, you get 3 over x. So this is the derivative. The derivative of a function in general is a function that represents the slope of the tangent line to the graph of your function as a function of x. So if you want to get the slope at a specific point, you need to insert into x in the derivative the axis of the point. The point is x0 equal to 1, so insert here into x1, so f prime of 1 means 3 over 1, which is 3. Which is the intuition, guys? Suppose, guys, this is stupid. Suppose that I tell you something stupid. Suppose that this function represents, I don't know, the profit of a given firm. Okay, a stupid example. Suppose it's the function, and suppose this is the price of the product. Okay, the price. The variable representing the price of 1 unit of product. Okay, and suppose that is the function that gives you, I don't know, is the price. And suppose that this gives you, I told you, the profit. So it's really stupid things that it does not even make sense. So which is the intuition, guys? I mean, it's a really stupid example, okay? It does not make so much sense, but which is the intuition? The intuition, no, only to say an intuition. If the current price is 1, and if you increase the price by 1 unit, that is, you pass from 1 to 2, the increment of the profit of the firm is 3. Okay, but I repeat, I know that cannot be a profit function, but I simply want to tell you which is the meaning, the intuition. This means, I repeat, that if you increment x0, which is this one, which was 1, you increment it of another unit, that is, for example, you increment the price from 1 to 2, then the increment in f in the function, suppose the profit, expected is 3. This is not the true increment of the profit, is not the true increment of the function, but it is the increment estimated if you move yourself along the tangent line to the graph of this function at the point x0 equal to 1. These are the things that I repeated so many times this morning, and I try to repeat now with this example, but okay, a stupid example, the one I just did, but to get the intuition. Okay, suppose you have this function. Compute again the slope of the tangent line at the point x0 equal to 1, or the instantaneous growth rate at x0 equal to 1. What you have to do? You have to compute first the derivative of the function, then you have to evaluate the derivative of the function at the point x0 equal to 1. I selected x0, guys, equal to 1, but suppose that, on the contrary, the price is 10, suppose x0 is 10. If I told you x0 10, you have to put here into x, you have to put 10. And remember, suppose it was 10, okay, this one. Suppose you made the computation with 10. So f prime of 10 would be 3 over 10, okay? So which would be the interpretation on the previous case? If you increment x from 10 to 11, the expected increment in the value of the function is 3 over 10, okay? So what I'm saying is that the increment is always 1 unit, okay, when you provide the interpretation of the slope or instantaneous growth rate. The increment of x is always 1 unit. x0 could be 100, 1 million, minus 1, it depends on the exercise or in the problem. Okay, so compute the derivative now. What kind of function is this one? F of x to the power alpha. So the derivative is alpha times f of x times what? The inner derivative, I mean the derivative of this one. Which is the derivative of x? 1. Please, we derived already square root of x several times. Believe me that this derivative is 1 over 2 square root of x. So we don't compute it again because we computed already several times by writing it as x to the power 1 over 2, and then we did already all the computation. So we did already. Now I told you we want to evaluate the slope at the point x0 equal to 1, so put 1 here, 1 here, 1 here. So 1 plus square root of 1 is 1 plus 1, 2. 1 plus 1 over 2, I made the common denominator, do blah, 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 and you get 6. So which is the interpretation? 6 is the slope of the tangent line to the graph of this function at the point x0 equal to 1. Is also the instantaneous growth rate of the function at the point x0 equal to 1. So which is its meaning? It means that if we are at x0 equal to 1 and we increase x from 1 to 2, that is, we increase x on 1 unit, we expect an increment of x of the function, of 6 units. But this is only the estimated increment. It's not the true increment, because in order to compute the true increment, you should look for the new value of the function. Instead, here we are moving yourself along the tangent line. Oof. Okay, guys. Another example. Let me drink. Sorry. Find the equation of the tangent line to the graph of the function f of x 5 plus ln of x at the point x0 equal to 1. So in this case, guys, I asked to find out the equation of the tangent to the graph of our function. So you don't need to find only the slope, but I want really the function, the straight line, the equation of the tangent line. Guys, we did it already. No, we did it already. Guys, I have already shown you yesterday or the day before. Remember that we reviewed the straight line. I have shown you how to find the equation of the straight line when you have 2 points belong to the straight line, or you know the slope, or you have either if you have an information allowing you to get m directly, the slope, and then to find q because you have the knowledge of 1 point. Here is the same problem. Why? Remember that those days, that day I told you Suppose I give you the notion of parallelism or perpendicularity. In this case, we have the notion of derivative. So find the equation of the tangent line to the graph of this function at the point x0, 1. We have everything. Why do we have everything? First of all, now we have a new way to find the slope, because we want to find the slope of the tangent to the graph of this function. So first of all, I compute the first order derivative of this function. The derivative of phi is 0. The derivative of ln of x is 1 over x. So this is the first order derivative, which represents the slope of the tangent line to the graph of this function as a function of x. But I want a specific tangent line, so I want a specific slope. I want the slope of the tangent line to the graph of this function at the point x0 equal to 1. So I need simply to insert, as we did in the previous exercises, 1 into x, and I get 1. F prime of 1 is 1 over 1, which is 1. And what is it? This is m, is the slope of the line we want to find. It's the slope of the tangent. But how can we find now the tangent? We have another information. We know that the tangent we want to find is tangent at the point x0 equal to 1 to who? To the graph of this function. What does it mean? What does this mean? This means that our straight line touches the function at this point. So this means that at x0 equal to 1, our function is touched by the tangent. So the value of y or f of y of both the function and the tangent is the same. So which is the tangency point? You have simply to insert 1 into your function. So compute f of 1, and then you get 5 plus ln of 1. But ln of 1, you know that is 0. Logarithm, independently by the basis of 1, is 0. So you get 5. So we find out that, so look, read with me because I wrote everything so you can pay attention. We need to find the equation of a straight line of the tangent, which is the general equation in explicit form, y equal to mx plus q. And we know already that m is 1, and we know that the tangent, since our function is, our straight line is tangent to the graph of this function at the point x0 equal to 1, the corresponding value of y is 5. So this means that our function is, our straight line is tangent to the graph of this function at the point of coordinate 1, 5. So do the system as we did 2 days ago. You have m equal to 1, then substitute the coordinates of this point inside this equation. The axis is 1, so put it into x. The ordinate of the point of tangency is 5, put it here, so you get 5 equal to m plus q. Okay, so put 1 into m into the second equation. I mean, I don't need even to read. So put 1 here, you get 5 minus 1 is 4, 4 equal to q, so 4 equal to q implies q equal to 4. So m is 1, q equal to 4. So substitute back m equal to 1 here in the general equation of the straight line, q equal to 4 here, and you get the equation y equal to x plus 4. So this is the equation of the tangent line to the graph of our function at the point. So you see, you have simply first to find m. In which way? Compute the derivative, then evaluate the derivative at the point. Then you have to find the point, the tangency point. Okay, since the tangency point belongs to both the straight line and our function, since I gave you only the axis, substitute the axis here to get the corresponding value of y, which is 5, and this is the tangency point. So you have the slope, you have a point belonging to the straight line. You can do what we have already done in the first lecture, in second lecture first, I do not remember, and you get the equation of the tangent line. Now, another exercise. Compute the instantaneous growth rate function. So we want to compute the instantaneous growth rate function, the relative instantaneous growth rate function, and the elasticity function of f of x equal to e to the power x. I did not ask you to evaluate the instantaneous growth rate, the relative instantaneous growth rate, and the elasticity at the given point. But I asked you to find the functions. So the procedure is even shorter, because which is the instantaneous growth rate function, guys? The instantaneous growth rate function, which is the instantaneous growth rate, guys, at a point, is the derivative evaluated at the point. So it's the slope of the tangents at the tangent at the point. So which is the instantaneous growth rate function? It's simply the derivative, because the derivative is what? The derivative of a function represent what? The slope of the tangent as a function of x. So it represents the instantaneous growth rate as a function of x. So the instantaneous growth rate function is simply f prime of x. So therefore, which is the derivative of the exponential of x? Is simply e to the power x. Which is the relative instantaneous growth rate function? Well, the relative instantaneous growth rate at the point x0 is f prime of x0 over f of x. I introduced this morning, okay? So since I asked the function, I don't need to substitute, I don't have to substitute a particular value. I simply have to compute f prime of x and to make the ratio with f of x. So which is f prime of x? F prime of x is this one, e to the power x, over f of x is e to the power x is 1. So the instantaneous relative growth rate function is 1. Okay. Which is the elasticity function? Remember, the elasticity, I introduced this morning, is f prime of x 0, if evaluated at the point x0, divided f of x0 times x0. In this case, since I asked the function, you don't have to insert a particular value of x 0 into x. So f prime over f of x has been already computed, which is 1. Okay, here I wrote it again, but who cares? Times x. So you have simply 1 times x, so the elasticity function is x. I call the elasticity function in this way. I don't know in the book how can you call it, EL f of x to mean the elasticity function of f of x. Now we're going to see other exercises, guys. Yes, since I have just shown you an exercise, first I want to do this one and then we go back to do the other. Example, find the elasticity of f of x equal to a x to the power b, where a and b are given numbers, are constant, and a is different from 0. So you see a and b belongs to R with only with additional condition that a must be different from 0. Otherwise you have, guys, 0 times something, which is 0. Okay, now compute the elasticity. Here again, I didn't ask you to compute the elasticity at a particular point. So apply the definition. The elasticity is given by f prime of x over f of x, which is the relative instantaneous growth rate function times x. So which is f prime of x? Compute the derivative with me. So a is a multiplicative constant, copy it. X to the power b is a power function. Remember, is the derivative of x to the power alpha. So it's alpha, in this case b, raised to times x to the power alpha minus 1. So b minus 1. Divided f of x itself. So copy ax to the power b. Times what? Times x. Before simplifying, you can observe that here you have the product of two powers with the same basis. So x to this power times this one is x to the power b minus 1, which is the exponent of x, 1. So x to the power b minus 1 plus 1 is x to the power b. Copy ab. Then you see you can simplify this with this, a with a, and you get b. So the elasticity of this kind of function is constant. Now, which is the interpretation? Remember that this morning I told you which was the meaning of the elasticity. Read, if X increases of 1%, then the increase of f of x is about b%. So this is the interpretation of the elasticity. Okay, in general, and in particular, guys, you see that the elasticity is constant in this exercise. So it does not depend on the initial value of x, okay? Because in general, it depends on x, on the value x0, okay? But here, since we make the computation, we get a constant. This does not, in this case, it does not depend by the initial value x0. So this means that if x increases by 1%, this is the interpretation for elasticity, x increased by 1%, then this result must be divided by 100. This means that then the increase of f of x is b%. Guys, b%, please. B% does not mean that you have to multiply b by 100. It means that you have to divide b by 100. You don't have to multiply b times 100. B%, I repeat, no, because I saw so many times this mistake. B% doesn't mean that you have to multiply b times 100, but you have to divide b by 100. So an increment of 1% of x increases f of x of about b%. I wrote about b% because this approximation is based on the tangent line. But the approximation is good typically, no, depends. No, I don't want to say more. Okay, so now go back. We have this exercise, which is an economic example. So, but I do not remember it. Read it together. So an exercise of economics, only to play with economics, okay, to show something about economics. Assume that the demanded quantity for a given commodity is given by the following function. dP, this means d of p, is equal to 8,000 times p to the power minus 3 over 2. Guys, this is a function. It has nothing special. dP is like f of x, or dP is simply y. Okay, y, for example, okay, you see I wrote it here. Y equal to dP, so y equal to 8,000 p to the minus 3 over 2, and p is x. So p, the price, is the independent variable, and d is the dependent variable. Or if you want, you can see, remember, y is equal to f of x, so at the same time you can call dP as f of x equal to 8,000 times x to the minus 3 over 2. Okay, but since we are working with the, I denoted this to mean, guys, that the demanded quantity, so the demanded quantity depends on the price. So this means the demanded quantity as a function of the price is equal to 8,000 times the price raised to the minus 3 over 2. The question is, compute the elasticity of dP, compute the elasticity of the demand, and find the percentual change in the demanded quantity when the price increases by 1%, and the price is P equal to 4. So I explained, I asked here to compute the elasticity of this function and to find the percentual change in the demanded quantity when the price increased by 1% and the current price, this means the actual price, is 4%. So this should be our x0, we called it before, so P0. So what does happen to the demanded quantity when the price goes from 4 to 4 plus 1% times 4? Okay, I show, okay, the computation. What does happen to the demanded quantity? So first of all, however, I asked you to find out the demanded, the elasticity. Well, the elasticity of the demand is simply, guys, what? Is simply given by the derivative of the demanded quantity with respect to P over the demanded quantity times P. We apply the derivative, the definition. You see, I wrote it before. Okay, I wrote it here. So to compute the elasticity of the demand, I need first to compute derivative of the demanded quantity with respect to the price. So this was our function, demanded quantity function, this one. So copy this multiplicative constant. What kind of function is this one? P to the power alpha. So it's x to the power alpha. So it's like x to the power alpha. Okay, so you have -3/2 times what? Okay, copy the multiplicative constant. P raised to the power alpha -1. So -3/2 -1. Okay, here then I did the computation. -3 times 8 is -24. Divided by 2 is -12. Add the 3 0. Then make the common denominator, and you get P to the -5/2. Okay, now we can compute the elasticity of the demand. You have simply to insert in here this quantity, which is the derivative. Here you have to insert instead the demanded quantity itself, so function, times P. So you see I simply inserted this one, I inserted this one, I multiplied by P. Then you see that you can simplify this 0 with this 0. You can divide by 4, you get 3 here. You divide by 4, you get 2. Okay, for this reason you see I wrote -3/2. Then guys, look what you have here. You have P to the -5/2 times P divided P -3/2. Oh, guys, this is a property we saw yesterday, because remember, if you have a product of two powers with the same basis, the result is the power with the same basis and the sum of the exponents, so -5/2 plus 1. Furthermore, remember that if you divide a power by another power with the same basis, you have simply to do what? The result is a power with the same basis, P, and what? And you have to sum, and you have to add the exponent in the denominator, but change by sign. So you have -3/2 times P to the -5/2 plus, you see I change by sign, 3/2 plus the exponent of P, which is 1. Now, if you make the common denominator and you make the sum, you have -5 plus 3 plus 2/2, so P to the power 0. So P to the power 0 is 1. So you get -3/2, which is equal to -1,5. So what did happen? Isn't interesting? Again, also in this case, but this is not always the case, also in this case, the elasticity, as in the last case, guys, the elasticity here was a constant, and here is also a constant. Guys, can you imagine why? Wait a moment. Look at the function. Here you had a constant times a variable to the power a constant, and we got a constant. Look at the function. The demand function here is exactly the same demand function, because you have A here is 8,000, X here is called like P, and B is -3/2. Obviously, this is a demand function exactly of this type. Power function times a constant, and what you get is, as elasticity, you get exactly B. In fact, look, we got -3/2. -3/2, guys, is exactly this number B. So this plays the rule of A, this B, and we got that this one. So we got that elasticity is constant. How can we, so you see, I observed it, note that the elasticity is constant and it does not depend on P. Okay, so which is the interpretation, guys? I wrote it here, so we read. Thus, an increase of 1% in the price of the product produces a reduction of the demand of about -1.5%, because I told you, you have to say 1% and this number divided by 100, so -1.5%, but you have to do it only for the elasticity. So a reduction, so an increase of the price of 1% produces always a reduction of the demanded quantity by -1.5%. Question, why I said always? Since this is constant, you see it does not depend on P. So this estimate, pay attention guys, okay, I know you are dying, but this estimate does not depend on the current level of the price. Why? Because we got the elasticity is constant. I'm asking you. So here I asked you then, the question was compute the elasticity, we did it. And I asked you, find the price, the percentual change in the demanded quantity when the price increases by 1% and the price is 4. Did I use the information 4? No. Why? Because here, guys, by computing the elasticity, I simply got the information that independently by the current price, if you increase the price of 1%, the estimated change in the demanded quantity is minus 1.5%. But here, so this is an approximation. Here, however, I asked for the elasticity and to find the percentual change in dP when the price increases by 1% and the price is 4. I didn't ask for an approximation. So we can try to compute now the exact percentual change in the demanded quantity when the price starting from 4, it increases by 1%. And we can then compare this result with the approximation that we got by using the elasticity. So if the price increases by 1%, then the new price will be given by what? The old price plus the change delta. This is delta. The change in the price. The old price, which is the current, guys, is 4. What does mean that you increase the price of 4%? That of 1%. You have to do plus 4 times 1%. Apply the 1% to 4. Okay. So 4, guys. Okay, 4 plus 4%. So it's 4.04. So what I want to get? I want to get the exact percentual change in the demanded quantity as the price increases by 1% starting to 4. That is, what does happen as the price goes from 4 to 4.04? Well, in this case, I ask you, which is the change in the demanded quantity? Which is the exact change in the demanded quantity? Well, I wrote delta dP is given by the demanded quantity when the price is 4.04 minus the demanded quantity when the price is 4. So you have simply to insert into the, okay, okay. You have, the function was, demanded quantity was 8,000 times P to the minus 3 over 2. So substitute into P the new price after the change, minus the demanded quantity when the price was 4, so minus 8,000, insert into P4 to the minus 3 over 2. What you get is minus 14,81. So the demanded quantity decreases if the, if the price increases of 1% starting from the current price of 4, the demanded quantity decreases about of 14,81 units. But which is the percentual change, guys? This is the absolute change. You have to divide the absolute change by what? By the current level of the quantity demanded, which is D4. So D4 is this number. If you substitute this number, so you have the absolute change in number of units divided the current value of the demanded quantity, you get minus 1,48. So if you look, this is what? This means that the exact reduction of the demanded quantity, if the price increases by 1%, starting from a current price of 4, is minus 1.48%. Minus 1,48%. If you go back, this is not far from the approximation that we got by making use of the elasticity, because we got the elasticity was minus 1,5, and in fact, you see, I wrote that minus is approximately equal to the elasticity divided 100. Now, why here I wrote 1000? What is it, this 0 here? Okay, divided 100. Okay, so But as you see, the elasticity here does not depend on the current level of the price. On the contrary, if you make the exact computation, this depends on the level of the price. Okay, guys, stop. 60 minutes earlier because we finished this exercise. Tomorrow, we will see if we will do something about limits, but I don't know because sometimes there are more important things to do. Okay, so now you can make practice, but tomorrow we continue with differentiation, okay? Increasing, decreasing function, concavity, convexity, etc., etc., etc. Okay, so guys, well, I told you at the end you have tons of exercise if you want to make practice. Okay. Okay, guys. Are you still alive? No, no. Are you tired? Yes, obviously. Okay, guys, do you have question for me? If you have question, you can ask. Otherwise, you can go with freely.
Okay, thank you.
Okay, thank you. No, okay, thank you.
No question, thank you.
Oh, no question. Bye. Thank you.
Thank you. Bye.
Thank you. Bye.
Bye. Bye. Now I answer to a guy who asked me something. Bye. Bye, guys. Bye all.
Thank you. See you tomorrow.
Thank you. Bye. Bye.
Thank you. Bye. See you tomorrow.
See you tomorrow. Thank you. In a moment, I answer you, Daniel. Bye. Bye, all guys. So, Daniel, you asked me. We use both elasticity formula and the second one formula by which we retrieve. Yes, in this exercise, guys, the elasticity allows you to make quicker computation. It provides you synthetic information. Then the second formula, I did it to get the exact change. And because I wanted to show you that the approximation of the made by the elasticity was good enough. Okay, but then it depends because this is more related to economics and I'm not a professor of economics. So if you have economics or something like that, it depends in the question. But here I wanted to show you mathematically in order to make the comparison between the approximation obtained through the elasticity, which is based on the approximation along the tangent line. Thank you, Lorpu. Thank you. Bye. Bye. But then I wanted to show you the exact change. Okay, because you can compute, if you have a function, you can compute also the exact change. Okay, so here I did both. Okay, Daniel.
Yes, thanks.
Okay,
Yes.
thank you. Okay, other question, guys? I do not hear. If you have questions. No question.
Yes, sorry, Professor, I have a question, but
yes, you can ask me. Yes,
almost personal because I have never done it like mathematics at all because I come from languages school.
Oh, so you need
yes, it's like very useful for me, and I would like to ask you like what I can do because the derivatives and all this stuff, it's like very difficult for me. So would you recommend to start like reading all the slides about the differentiation, or do I need something else?
No, for me to learn it is enough. First of all, yes. If you have problem with derivatives, this means that is the most important thing you need to study. Well, it is important that you first of all you understand the meaning. But I think if you study, you don't have problem to learning the meaning because I told you which were the more important things. I do not recommend you to read all the slides because there are explanations which can be more complicated because they are linked to limits. I suggest to review only the things we did together first. Then what you have to do, you have print the page containing the derivative. Okay. Take it next to you, and then now I still open the file. Then after having reviewed review first by using this sheet of paper next to you, review first all the derivatives we have done together. Then after having reviewed that, you have tons of exercises here from page 18, and you have concerning the derivative computation. Then try by your own to do these derivatives, and after having done them, you can check the solution. So for example, you can do one derivative, then check the solution, one derivative, then check the solution, because there are almost all the steps. There is not only the final result, but all the relevant steps. Okay, So what I suggest, print first, okay, review the concept of slope, which means the slope, the instantaneous growth rate, look at the graph. But I know that for Roberto 10, for the course, you must be able to compute derivative. So I suggest really to print this page, I mean, what is the page?
The one with the rules.
Well, the one with all the rules, with all the rules, then review all the exercises with it together with the rule next to you. Okay, so you try to understand, if you forget, which rule did we use, and look, and then from the solution, try to understand if you're able to find out which is the rule. But if you're not able, then look also at the solution, and by looking at the solution, you should be able to understand which of these rules we followed. So first review with this table all the rules we did, all the derivative we did. Then do all the other you have for home. Obviously, you cannot do it today because you have so many exercises. Okay, you have too many, but do every day something. When you have time, do some derivative every day if you can. Okay, 1 hour, 1 hour, yes, 1 hour of derivative, because the derivative are very, very important. Okay, and at a certain, and when you do the derivative for home, do the one I gave for home. Do one derivative, then go to the solution to check if you did it correctly. If you did not do it, I mean, if you did it wrong, check the solution and understand the solution. Then go back, do the second derivative for home, then check it. Okay. But first try by your own to do it. Okay. First, you have to try to do it by your own.
Yes, I have to try to study like a little bit more the rules before, and then I try to do some exercises.
Yes, but first start by reading the rule and keep them with you, because first you have to understand the mechanism also, the rule and the mechanism.
Because today sometimes I got lost since it was like fast since I.
No, but I understand if you have never done it, it's obviously it's a crash course, 6 hours a day, you are done. You know, but I know it would have been difficult also for me if I knew nothing. Okay, so I understand. So don't be scared, because I repeat, you need to make exercises. Don't do a lot of things every day. First of all, you have a lot of class. I mean, you have a lot of time to spend by paying attention to lectures. So, but when you have tried 1 hour a day, I don't know, 1 hour, maybe in the weekend if you have time, maybe more than 1 hour. I can. Okay. But I do as I told you. So don't study all the slides, no. Because to understand the slide, you need then also to study. Yes, you need also the limits, which are in slides number B. Okay. Unless you want really to study really all my slides, I suggest to start directly from the formulas, because I mean, the theoretical explanation is useful to understand better the concept, but not for applying the formulas. To apply the formulas, you need to work with this table. Okay.
Thank you very much.
Oh, welcome.
Thank you.
Don't be scared. Guys, do you have other question for me? No. If you have no question, I go, because in 5 minutes I have another lecture at 5 minutes, 8 minutes. Okay. So see you tomorrow if you want. Bye, guys. I stop recording. Okay. Yeah.